Chapter 12, The Matrix, Before the Movie. In this chapter, we will examine the matrix, which is an interesting data structure. It is a two-dimensional holder for variables and it is best understood as a grid or table. You will learn how to assign values to each spot in the matrix, as well as learn how to retrieve values already stored in it. The last thing we will examine is the diagonal, an important part of the matrix. In this chapter, the grid of rows and columns, loading one row at a time, nested for loops, manipulating a matrix, the diagonal of a matrix, the matrix as a grid. Now that we have studied the array, it would be good to examine the matrix, which is the name given to any multi-dimensional array. You might recall from an Algebra 2 class the word matrix. Matrices look like grids. See Figure 12.1. Figure 12.1. A two-dimensional grid with 3 rows and 4 columns. Each slot in the grid has a numbered location, and this is why matrices are a good place to store data. See Figure 12.2. Figure 12.2. Each slot has a unique location, its row followed by its column. Each of the locations is unique because of the row and column, which vary for each slot. Look at slot 1, 1, and think of it as the first member in the first row and first column. If you look at slot just to the right of it, it is numbered 1, 2. You can think of this as the second member in the first row. Slot 1, 3 is the third member in the first row. If you skip down to slot 3, 1, you can think of this member as the first member in the third row. Now let's give a name to this matrix, just as we gave a name to the arrays we examined. We could call it student. See Figure 12.3 for one interpretation of the grid. Note that the grid serves to illustrate how the values in a matrix are organized. Figure 12.3. The grid is shown filled with different students identified by their row and column. So the top left is student 1, 1. Diagonal to that is, completely down from that is student 2, 1, and completely to the right of student 1, 1 is student 1, 2. Each student is identified by the two numbers which could represent where they sit in the class. Student 1, 1 is the first student in the first row, while student 2, 1 is the first student in the second row. Then student 3, 2 must be the second student in the third row. See Figure 12.4. Figure 12.4. Each student is sitting at a different desk and identified by location instead of a name. As mentioned earlier, computers lack imagination. It is easier to use numbers to identify elements than individual names. When we studied the array, we looked at each part of the array as a separate numbered slot with a common name. Do you recall how we called one array group? Each of the members were named Group 1, group 2, group 3, group 4, and so on. The nice thing about the array was that we could easily distinguish among the different group members because of the subscript attached. Think of all the friends you have with the same name, Mike, for example. I have a lot of friends named Mike. The way I think of each Mike in my head is to distinguish each one. I think of the Mike who takes the same math class as I do, the Mike I work with, the Mike who is my cousin, and the Mike I met over the summer. In computer programming, these distinctions are made as a matter of fact and with less description. Mike 1, Mike 2, Mike 3, Mike 4, and so on. And these would be written as follows: Mike 1, Mike 2, Mike 3, Mike 4. Where Mike 1, Mike 2 is below Mike 1, and so on and so forth. So the array we talked about previously in Chapter 8 is a nice way of recognizing that there is a common name for the variable holders, but each holder is also unique. Before we look at the matrix in computer terms, let's examine it from the perspective of algebra. The matrix. The matrix is a grid where each slot has a unique location, and the location is numbered according to where it is in the grid. A matrix is a really nice holder for data. It allows several values to be stored in one place under a common name that reminds us that the data is grouped together. In Algebra 2, matrices are often used to store coefficients of variables in equations. The matrix is a great storage facility. It can be used to calculate the determinant. Whether you have learned this yet or not, the neat thing is that understanding what a matrix is in computer programming will make it easier for you to understand its use in algebra. Let's revisit the student matrix we talked about. Note, in most computer languages, a matrix has a row 0 and a column 0. We have ignored that to simplify the discussion. See the program on the CD for examples of those matrices. Let's look at how each member would be named in a computer language. Name, computer language. Student 1, 1, student 1, 1, student 1, 2, student 1, 2, student 1, 3, student 1, 3, student 1, 4, student 1, 4, where the difference is the first one they're just without brackets, and the second example they're with brackets. As you can see, the first subscript is 1, and the second changes from 1 to 4. As a matter of uniformity, the first number represents the row number while the second number represents the column number. So when you declare a matrix to the compiler, which is compiler, you tell the computer how many rows and how many columns your matrix will have using the same brackets we used when we declared an array. 3, 4, both are in brackets. So now the matrix has 3 rows and 4 columns, like we discussed. In each of the examples that follow, we will make different declarations for different matrices. It requires a special declaration, just like the array we studied previously. If you recall, with the array, we had to state the name or identifier and then how many members it would have and what type of data it would hold. Int list 10. This array is a declaration of 10 members holding integers and all with the common name of list. The matrix will follow a similar syntax. Int group 6, 4. Here we have a 6 by 4 matrix that will hold integers and will have the name group. Here's another example of the student matrix we discussed previously. String student 3, 4. So the student matrix has 3 rows and 4 columns, and each holder will contain a string. Think of the string as the name of each student sitting in the class at the assigned seat. Consider this example. Double prices 5, 5. This represents a 5 by 5 matrix where the name, print prices, and containing doubles real numbers. How does storage work? So with the previous examples, we have informed the computer what kind of data holder we need and how many slots of memory we need as well. In the example with the student matrix, the computer has to set aside enough storage to hold 12 different strings. Each string will take a fixed number of bytes for storage, so 12 of those strings will take 12 times that number bytes of memory. Recall that that is the most important reason for the declaration of variables. We need to tell the computer how much memory it should set aside or allocate for the data we have. In the other example, where we declared the group matrix, we needed to have 24 slots, all with the common name of group and each holding an integer. If each integer needs 2 bytes for storage, then 24 of those integers will take 48 bytes of storage, and the computer will look for 48 sequential free bytes once the declaration has been made and the program starts to compile. Loading one row at a time. Consider this example where we will load the following. Int group 6, 4. We know we have 6 rows and 4 columns. Let's start by loading the first row only. And to make things easier, let's put the same number into each member of the first row, like this. Column 1, column 1, column 2, column 3, column 4. Row 1, for column 1, group 1, 1, column 2, group 1, 2, column 3, group 1, 3, column 4, group 1, 4. Data inside goes in the order 5, 5, 5, 5. If we were to load the row manually, we would have to write this code. Row, column, group 1, 1, 5, group 1, 2, 5, group 1, 3 equals 5, group 1, 4 equals 5. So instead of typing each member separately, let's use a for loop to hit each of the members in row 1. Here is the for loop that will do that. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace, group 1, x equals 5, closing brace. I have only used one for loop, just so that we can see that we are only loading row 1 across. Notice that I referred to the row as group 1x. The reason I did this was because I wanted to stay in row 1 and then move across each of its columns to load each member in that row. The X represents the changing column. It is helpful to keep the classroom seating plan in mind as well as we work with the matrix. Let's try to load all the members who are sitting in row 2, and let's load those members with the same number. Let's put the number 10 into each member of the second row. Column 1, column 2, column 3, column 4, row, column 1, group 2, 1, column 2, group 2, 2, column 3, group 2, 3, column 4, group 2, 4. Data inside, 10, 10, 10, 10. If we were to load the row manually, it would look like this. Row, column, group 2, 1 equals 10, group 2, 2 equals 10, group 2, 3 equals 10, group 2, 4 equals 10. We can now use the same code as before, with only a couple of alterations, changing the row we are interested in loading, as well as the number we want to store into the matrix. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace, group 2, x, closing brace. On the CD, see each of these examples written in Java, which uses the 0 subscript. Nested for loops. Before we examine the array further, let's look at nested for loops, which will prove very useful in working with a matrix. There are two loops in a nested for loop, the inner loop and the outer loop. To understand the two loops better, let's examine a bicycle and its gears. The bicycle gear analogy. Think of the outer and inner loops as gears in a bike. On a 10 speed, you have 2 outer gears and 5 inner gears. You see the outer gear to one of 2 choices. You set the outer gear to one of 2 choices. The smaller one is for hills, and the bigger one is for flat riding. You have a choice of 5 different speeds for the inner gear and 2 different speeds for the outer gear. Let's say you want to test all 10 speeds that the bike has. You decide that you will methodically test them in an organized sequential manner. So you decide to set the outer speed to the hill setting, and then try each of the inner gears with that hill gear. This is a list of the speeds that you are testing. The hill gear will with the inner gear number 1, the hill gear with the inner gear number 2, the hill gear with the inner gear number 3, the hill gear with the inner gear number 4, the hill gear with the inner gear number 5. Notice how the hill gear does not change, while the inner gear does change. This will be important when we look at nested loops. We have methodically exhausted all of the inner gears with one of the outer gears. Now, if we change the outer gear to the flat surface gear, we can do the same process again and test 5 more speeds on the bike. This is a list of the rest of the speeds you are testing. The flat surface gear with the inner gear number 1, the flat surface gear with the inner gear number 2, the flat surface gear with the inner gear number 3, the flat surface gear with the inner gear number 4, the flat surface gear with the inner gear number 5. Notice how the flat gear doesn't change at all as we change the inner gears. So for each outer gear, we used 5 different choices for the inner gear. Let's summarize what the different possibilities for each gear were. Outer, inner. Hill, 1, 2, 3, 4, 5. Flat, 1, 2, 3, 4, 5. For each outer gear, the inner gear had 5 different choices. As we test each choice of the inner gear, we make a complete spin through the options. What do I mean by this? For example, the outer gear was in the hill setting, while the inner gear spins from 1 through 5. Applying the loops. Let's write some pseudocode to represent the gear settings on the bike. Recall that pseudocode is not real code, just an approximation of real code. For x is equal to hill setting, x is less than or equal to flat setting, x plus plus. For y equals first gear, y is less than 6, y plus plus, test gear. Look at the preceding code. The outer loop with the variable x will be set to the hill gear, and then the compiler will enter the inner loop because that is contained within the body of the x loop. But there is another loop inside the x loop, and that is the y loop. Since the y loop is completely contained within the x loop, the y loop will spin completely from 1 to 5. Once the y variable hits 6, the y loop will stop executing and control will bounce back up to the last statement of the x loop, x plus plus, where x's value will change from hill gear to flat gear. Once the x variable changes and is checked to be valid, that is, the Boolean statement is true, then the y loop is entered again and the y value is set to 1 as it was the first time. This is how the other 5 speeds get set. So now all 5 speeds will be paired with the x value of flat gear. Our next step is to examine a matrix and to use what we call nested for loops to load the matrix. The term nested means that we will put one for loop inside the other. Before I explain what this does, look at this code. For int x equals 1, x equals less than or equal to 5, x plus plus. For int y equals 1, y is less than or equal to 4, y plus plus, opening brace, group x, y equals 5, closing brace. The loop that we see first is called the outer loop. The loop that is second is called the inner loop. The way I like to think of the outer loop is that it is the driver of the inner loop. The outer loop engages the inner loop in the same way that a driver engages the shift to cause the gears to engage. So let's watch the computer step by step to see what I mean when I say that the outer loop controls the inner loop. For int x equals 1, x is less than or equal to 5, x plus plus, the outer loop sets x to the value of 1. Then the inner loop starts to spin for int y is equal to 1, y is less than or equal to 4, y plus plus. Opening brace, group x, y equals 5. Remember that x has the value of 1, closing brace. So the outer loop sets x to 1, and then the inner loop starts to spin. The inner loop will spin, and y will go from 1 to 4. Look at the chart of values of the variables. X, then y. 1, no value. 1, 1, 1, 2, 1, 3, 1, 4, 2, y's blank. On the last line, we see that x becomes 2, and the inner loop that controls y will start to spin again. Now look at the chart with the variables. X, y. 1, no value. 1, 1, 1, 2, 1, 3, 1, 4, 2, no value. 2, 1, 2, 2, 2, 3, 2, 4. So what happens is the outer loop holds its value, while the inner loop spins through all its values. The entire execution of both loops looks like this. X, y. 1, no value. 1, 1, 1, 2, 1, 3, 1, 4. Blank x, y is 5. Y becomes 5, and so the value is too big for the loop condition to be true. The y loop stops. The x loop then changes its value from 1 to 2 and executes again. Because the y loop is inside the x loop, the y loop starts to spin again. X, y, 2, 1, 2, 2, 2, 3, 2, 4, x is blank, y 5. Notice that y again changes its value to 5, and its Boolean condition is not true. Also notice that, while the y variable is changing its value, the x value is not changing at all. This is because the end of the x loop has not been reached. Its value cannot be increased until all its statements within are executed. Notice that the statements inside the x loop are the body of the y loop. X, y. 3, blank, 3, 1, 3, 2, 3, 3, 3, 4, x is blank, 5. 4, blank, y. 4, 1, 4, 2, 4, 3, 4, 4, blank x, 5. Then 5, blank y, 5, 1, 5, 2, 5, 3, 5, 4. How to store data in a matrix. Now that our declarations have been made, let's consider how we might store data into each slot of the matrix. When we worked with the array, we used a for loop to load each slot of the array. We will do the same thing with our matrix, except that we will do the same thing with our matrix, except that we will need 2 for loops to load all the members in the matrix. For int x equals 1, x is less than or equal to 5, x plus plus, opening brace. The outer loop sets x to the value. Then the inner loop starts to spin. For int y is equal to 1, y is less than or equal to 4, y plus plus, opening brace. Cout. Please type a value for each slot. Cin, group x, y. Remember that x has the value of 1. Closing brace, closes the y loop, closing brace, closes the x loop. How to retrieve data from a retrieve data from a matrix. Now that we have loaded a matrix, let's check to see that everything we put into the matrix got sent in correctly. Let's start by checking row 1 of the group matrix to see if the first row contains 5s. We want to print out the contents of row 1. These 4 statements will show row 1. Cout group 1 1, cout group 1 2, cout group 1 3, cout group 1 4. It will look like this: 5 5 5 5. Let's follow the previous code with a line feed and the next 4 print statements. Cout end L, cout group 2 1, cout group 2 2, cout group 2 3, cout group 2 4. So now all 9 lines will produce the following output: the 5s from the first row, a line feed, and the 10s from the second row. 5 5 5 5, 10 10 10 10. If we had not put the cout and L statement in the code, all the numbers would appear in one line like this: 5 5 5 5 10 10 10 10. Now let's take the previous code and replace it with 2 for loops. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace. Cout group 1 x, closing brace. Cout end L. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace. Cout group 2 x, closing brace. Each loop spins through its row and prints each member. We could write 3 additional loops to print the other rows, but it will be easier to employ the nested loops we studied in the previous section. Look at this code. For int x equals 1, x is less than or equal to 5, x plus plus, opening brace. For int y equals 1, y is less than or equal to 4, y plus plus, opening brace. Cout group x y, closing brace. Cout end L. This line feed puts each row on a separate line. Closing brace. Manipulating a matrix. There are many ways to manipulate a matrix once it has been assigned values. We will look at some examples in this section. One of the main alterations you can make to a matrix is to change the values in one row or column. Another thing you can do is work with the diagonal of a matrix. These are a few ways you can manipulate a matrix. The diagonal. First, we need to define a square matrix. As its name suggests, it is a matrix with the same number of rows and columns, so it looks like a square. The diagonal is the diagonal line running through it from the top left to the bottom right. See figure 12.5. Figure 12.5. Each member along the diagonal line in this square matrix has the value 1, while the other members have 0. The diagonal members of a matrix are also interesting because of their locations. Look at the same matrix, but this time look at the locations rather than the contents. See figure 12.6. Figure 12.6. All of the locations of the matrix are given. Notice how the diagonal locations have matching rows and columns. So for instance, the first row has 1, 1, 1, 2, 1, 3, 1, 4, whereas the first column has 1, 1, 2, 1, 3, 1, 4, 1. If you want to access the values along the diagonal of a matrix, you insert a Boolean condition inside the nested for loop. Consider this example. For int x is equal to 1, x is less than or equal to 4, x plus plus, opening brace. For int y equals 1, y is less than or equal to 4, y plus plus, opening brace. If x equals y, see out, box x, y, closing brace, closing brace. Note that both x and y have an upper limit value, which is 4, indicating that the matrix is a square matrix. The Boolean condition, if x equals y, allows the programmer to select the member along the diagonal. The other members are ignored. How to change an individual row or column of a matrix. In order to alter a particular row or column, you need to spin a loop that holds that column or row fixed. To see what I mean by this, let's return to a previous example where we loaded one row, row 1, of the group matrix. Recall that the group matrix was a 6 by 4 matrix of integers. This information will be useful when we change a column instead of a row. For int x equals 1, x is less than or equal to 4, opening brace, group 1, x equals 5, closing brace. Notice that the row index, always the first index, is fixed at 1. It is only the column index that is changing. The x is being used as the variable that controls the column position. Right now, each member of row 1 is being assigned the value 5. Let's change the code so that we set all the values in row 1 to have the value 8. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace, group 1 x equals 8. We only had to change this line, closing brace. Let's say you wanted to change row 4 instead of row 1. We will change the fixed row from 1 to 4. Here is the code that accomplishes that. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace, group 4 x equals 10, closing brace. As you can see, we are assigning the value 10 to all the members of row 4. Look at the next example where we print all the members of row 5. For int x equals 1, x is less than or equal to 4, x plus plus, opening brace. C out group 5x, closing brace. The only thing remaining to do is to alter a column. Let's put the value 4 into the slots in column 3. Think of it this way. We need to fix the column and move down the column from row 1 to row 6. In order to do that, we have to change the for loop we are using to one that will target all the rows. Remember, it is a 6 by 4 matrix. Look at this example. 4 int x equals 1, x is less than or equal to 6, opening brace, group x3 equals 4, closing brace. Notice that column 3, as the second subscript, does not change. Only the rows change, since we have to move down the rows in column 3. Summary. In this chapter, we learned about the matrix, a two-dimensional grid which has a certain number of rows and columns. The matrix is ideally assigned through the use of nested for loops, one for loop inside of another. By using nested for loops, we can move through every member of the matrix. We examined the analogy of the gears on a bicycle, since holding one gear while changing the other is very similar to the way nested for loops work. After practicing some examples of assigning and printing the contents of the matrix, we also manipulated individual rows and columns as well as the diagonal of a square matrix.